In this video, I want to go over sections 17.7 and 17.8 very briefly. I don't want to go into great detail on them, but just kind of give you a feeling of how we can use our knowledge of sound waves in something very familiar to everyone, that is music. And so if we look at, say, a picture from the textbook, what you see is two cases. One where you have a pipe which is open at both ends, and one which you have a pipe which is closed at one end but open at the other end. So this kind of covers a variety of the musical instruments that you can make with pipes. So we're only talking about pipe instruments. We're not talking about strings or anything like that. But it still covers a long range of, from the organ to clarinets to saxophone to trombone, all the brass and the woodwinds, like that. So you'll notice with the pipes that have two openings to them that the wavelengths are at their maximum amplitude. The waves are at their maximum amplitude at both ends. With the closed pipe on one end, the wave starts at 0 amplitude at the closed end and goes to an open amplitude at the open end. And so with the pipe with two open ends, if you trace it out, you would get basically 2 wavelengths, or 3 wavelengths, or 4 wavelengths. And with the one where it is a one closed end, one open end pipe, then you would get basically half a wavelength, or 3 halves of wavelengths, or 4 halves of wavelengths. So basically you would get, for the pipe with the 2 open ends, you would get basically all the harmonics. But with the pipe that is closed at one end, open at one end, you would get, only get you only get the odd harmonics, because you get this half a wavelength. You only get the odds. So if we were to consider then this, very ready to summarize it. So 2 open ends, you get all harmonics. But basically you have to start with twice the length. You get 2 wavelengths for the length of the pipe. So basically, our wavelength that we can write down is twice the length of the pipe divided by some integer, where it is 1, 2, 3, so forth and so on. It would basically, we're starting with n equal 1 because really, if you look at it, we're starting with the second harmonic. Or the first harmonic, but there are 2 wavelengths. So we're starting with the second harmonic. So basically, that is the relationship between the pipe. So therefore, if we want to figure out what the frequency is, if you remember, the speed of the wave is the frequency times the wavelength. So now if we plug in what we have for the wavelength, we have twice the length of the pipe divided by n, which harmonic we're going to have in there. And so the frequency for this particular instrument would be n harmonics times the speed divided by twice the length of the pipe. Where now our index goes from 1, 2, 3. So we're not really considering n equals 0, even though it's possible. Then you just wouldn't have any sound. So for the 2-ended open pipe, you can figure out what the frequencies that are available by the length of the pipe. So you have to be able to fit the wavelength inside of that pipe. So, if you're designing a musical instrument, like a trombone, then you have to figure out what is the length of that total pipe that you have, and then you can adjust the length to get you, whatever wavelength you want to have inside that pipe. You also can consider the speed of the wave. A lot of times we're playing these musical instruments in air. So, sometimes you have to consider, the temperature of the air. But for the most part, it's just proportional to the speed. And then to get the different harmonics, you just figure out how many wavelengths you're putting inside that pipe. So a pretty simple solution. And again, just to kind of emphasize that the frequencies, F, are proportional, linearly proportional to the number of the harmonic there. So it's pretty easy to figure out, in terms of the length, if you you change n. The next harmonic is going to be twice the previous one. So, if n equals 1 is our fundamental, or our lowest harmonic, then we would just have F1, which would be the speed divided by twice the length of the pipe. And then for n equal 2, you just have 2 times F1. N equals 3, we would have 3 times F1. So working with frequencies, it's much easier to figure out what the different frequencies you need. They just go linearly. Now, if we had the single open end, like I said, you're going to start with a 0 amplitude, and then you're going to go to the full amplitude on the other side. Okay, so in this case, what we have is, if you count it up, let's start with the first one. That right there is would be basically a quarter of our wavelength, and so the wavelength would fit in a pipe that would actually be 4 times longer. If we go down now to that, so that would be the n equal 1. For n equal 2, now we get 1.5. Like this, and so that would, the wavelength, if we were to extend the pipe to get the full wavelength, it would be 4 times the length divided by 3. For n equal 3, you could draw it out, but what you would have is 4 times the length divided by 5, etc., etc. So in the end, what you would have is an equation where this wavelength is 4 times the length of the pipe divided by the number of the loops, basically. And so to figure out the frequency we said was just the velocity divided by the wavelength, 4L over N. So our frequency is the number, for the number of loops, times speed divided by 4 times the length. Which looks a lot like what we had before for the 2-ended open pipe, except now we have an extra 1/2 in there. We have 1/2 NV over 2L. It doesn't mean that, there's any relationship between the 2-ended open pipe and the 1-ended open pipe, except for the fact that we need 1/2, because we need an extra half a wavelength to, you need that extra half a wavelength for the pipe. So in the end, you get this formula that in order to calculate basically what the frequency is going to be given a length of pipe, you would just need to know the speed in air. I should mention, the ends now are different here in the fact that they're only odd. So what we could do is we could rewrite this, the book doesn't, but we could rewrite this as 2 times m plus 1 v over 4l, where now m goes from 0, 1, 2, so forth and so on. So you can write it either way. You can either know that you're only going to get the odd harmonics out of a single-ended open pipe, or you can write it down in this way. So it may be easier to use this equation right here, because then you know that you're only dealing with an odd number of harmonics. You don't get all the harmonics out of an open pipe. So if you're trying to figure out how to design your musical instrument, it may be easier to use the index n instead of the index m. Now for beats, what we have is basically 2 waves, so we can get 2 harmonics, 2 fundamental harmonics overlapping each other. And what happens is if you pick the harmonics just right, what you get is basically this kind of waveform that has built into it basically a larger waveform. So you would get something which now has kind of a composite wavelength inside of it. So the interference gives you something where now your ear is hearing kind of a larger wavelength. You're hearing this beat, even though it's comprised of 2 separate waves. So I'm not really going to go into the derivation, but what you end up getting is, if you were to write this out, you basically start with wave number 1, if they have the same amplitude, and we only look at the time dependence, then you get wave number 1, and it's got a wavelength frequency omega 1, and then you get the equation for the second wave with a frequency omega 2, and when you basically add them up, so S total is S1 plus S2, what you get is an equation that says S is twice the amplitude times cosine 1/2 omega 1 minus omega 2 times t times a cosine 1/2 omega 1 plus omega 2 times t. So if you multiply those two together. So you get this interesting effect where you basically get the beat frequency of 2 times 1/2 omega 1 minus omega 2, or basically just the difference between the frequencies. So if you're trying to plan it out exactly how to get that structure so it's nice and appealing to the ear, you could basically calculate the differences in the frequencies to get the beat. And since these omegas are just 2 pi times the linear frequency, then our beat frequency in hertz is just frequency 1 minus frequency 2. So now you can calculate how to get a nice pleasing beat out of a combination of fundamental harmonics from whatever instrument is that you're trying to play.